The topic of today is neural networks. My name is Johan Hagelbeck and I'm a senior lecturer at Linnaeus University. We'll begin by looking at a linear classifier. It will have two major components, a score function that maps the data to categories and a loss function that calculates the difference between predicted categories and actual categories in the training dataset. And the loss function will be used for training the classifier. So let's begin with the score function. We have a linear function where we multiply each weight with a corresponding attribute in the input data and add a bias. X is the input data with one value xi for each attribute, and each attribute is then multiplied by a weight wi, and finally we add a bias b. And the bias is needed so the linear function doesn't have to cross the origin. And the linear function is used to separate categories. So here we have two categories, the red A's and the green B's, and we see that we can find a straight line, a linear function that completely separates the two categories. And as the name implies, the linear classifier can only separate linearly separable categories. It will never be 100% accurate if we have a dataset that, for example, looks like this. There is no way we can place a straight line that completely separates the two categories. If we calculate the score function, where we multiply the weights with the attributes in the input data for an input instance, we see the confidence that the input example or instance belongs to that category. And higher values means more confidence that it belongs to that category. And this is our score function. But what if we have more than one category? If we have two or more categories, which we usually have, we need one linear function for each category. So the first linear function maps to the first category, the second linear function maps to the second category, and we have a number of linear functions for depending on how many categories we have. And the most efficient way to calculate the score function is to use matrix and vector operations. The weights can be seen as a matrix W, where we have a number of rows equal to the number of categories, and the number of columns equals to the number of attributes in our input data. And then we have a bias with a size of number of categories, and the inputs vector, which is the training example, and the size of the number of attributes we have in the training example. And calculating the score function is then a matrix vector plus multiplication plus addition. So we multiply the weights matrix by the input vector and add the bias. And this produces a vector with one confidence value for each category. And the example is classified as the category with the highest confidence using the argmax operation. And the argmax for a vector returns the index of the highest with the highest value in the vector, and that's our predicted value for this training example. So it works like this. Assume we have two categories and three inputs, so our weight matrix needs two rows, two categories, and three columns because we have three input values or attributes, and the input vector is three attributes. And when we calculate this multiplication, we get a new vector of size 2 because we have two categories, two rows in the weight matrix. And the first row is calculated as the first element on the first row in the weight matrix multiplied by the first element in the input vector, plus the second element of the first row in the weight matrix multiplied by the second element in the input vector, plus the third element in the first row of the weight matrix multiplied by the third attribute value in the input vector. And we do the same thing with the second category, where we multiply the weights of the second row in the weight matrix with the input vector. And when we add the bias vector, so we simply add the values of the bias vector to the previously result vector from the matrix multiplication. And this is actually the dot product of the input vector xi with each row in the weight matrix. So it's just a number of dot product operations we do. First we calculate the dot product of row 1 in the weight matrix with the input vector, then we calculate the dot product of row 2 with the input vector. And the number of columns in the weight matrix must be equal to the number of components in the input vector, because we need, of course, one weight for each attribute. We don't even need to split the input data matrix X into columns. When calculating a product between matrices W and X, we can see X as a bunch of lined up column vectors. So we multiply the weight matrix with the first column in the X matrix, and then we multiply it with the second column in the X matrix, and so on. And this results in a new matrix where we have each column in the resulting matrix is corresponding to each column in the input data matrix X, so corresponds to each of our training examples. And the bias vector B is then added to each column. Now we have a matrix where each column is a score vector for an example x, y in X. And taking argmax for each column produces a row vector with a predicted category for each example. So the first value is the argmax operation for column 1, which is our predicted category for the first training example. The second value is our predicted category for a second training example, and so on. So let's see a simple example. We have an input, which is a cat, and this cat is converted to a pixel vector. Only 4 pixels is used, so we compress the image quite a lot. We have a weight matrix that looks like this, so we have 3 categories, cat, dog, and rabbit, so we need 1 row for each category, and we need 1 column for each attribute, about 4 attributes. And we multiply the weights matrix with the input vector and add the bias, and we get a scores vector. And the highest value of the scores vector is the second position, which is a dog. So the argmax operation returns the second element, which corresponds to a dog. And this is clearly not a dog. The weights needs to be modified or learned to produce the correct output. So if we modify the weights slightly or learn the weights, we get, and we perform the matrix multiplication plus bias addition, and we get a new scores vector. And now the highest value is on the first position, which corresponds to a cat, and now we get the correct output, since this is obviously a cat. So the question is, how can we automatically learn weights from the training data? And this is where we need the loss function. So that's the first thing we need to define. And the loss function is sometimes called a cost function or objective. And it measures how happy we are with the result. The first set of weights for the cat image gave a poor prediction, and we're not very happy with the result. The second set of weights gave a good prediction. We labeled the cat image as a cat, so we're happy with the prediction. And the loss will be high for bad predictions and low for good predictions. And there are many loss functions we can use, but we'll focus on a very common one called Softmax. Softmax Softmax calculates the normalized probabilities for belonging to each category. This is then combined to a single loss value called the cross-entropy loss. And the loss Ly is calculated using the formula here. So we calculate the log probability for the correct category, EFYI, and normalize by dividing with the sum of log probabilities for all categories. And finally, we calculate the negative natural logarithm of the normalized log probability for a correct class. Now we get the total loss. So if we go back to our example, we have a set of weights in the weight matrix, and we have an input example with attributes, and the correct class is 2. And we have a bias vector. And we calculate the scores vector, and then we take each score and calculate E raised to the score value, and we get a new vector with a value of 0.058, 2.36, and 1.32, and then we normalize it by dividing with the sum of the EFJ vector, and we get the normalized scores 0.016, 0.6332, and 0.353. And when we calculate minus log for the correct category, which is 2 in this case, so minus log 0.353 equals to a loss of 1.04. And as we mentioned before, the matrix multiplication is the dot product. The first element is the dot product of row 1 in the weight matrix and the column vector xi. And we calculate the dot product, all 3 dot products, and we get the resulting vector. And in our case, it looks like this. So the first element is calculated as 0.01, the first element of the first row in the weight matrix, multiplied by minus 15, which is the first element in the input vector, minus 0.05, the second element of the weight matrix, multiplied by 22, plus 0.1, the third element of the first row in the weight matrix, multiplied by minus 44, plus 0.05, the last weight in the first row of the weight matrix, multiplied by the last element of the input vector, and this equals minus 2.85. And we do the same for the other 2 categories. And the matrix addition, we simply add each element of a bias vector to the resulting vector of the matrix multiplication. And we get the scores vector. If we have very high scores, calculating E raised to each score value and then sum all the score values can lead to numerical problems, and then we can have a problem called numerical stability. The sum can blow up, meaning that we get outside the range of double or float values depending on which ones we used internally. And this can be solved by shifting all scores so that the highest score is 0. So we first find the max in the scores vector and then subtract the max for each score. And now we have negative or 0 values that will avoid the problem of numerical stability. So, regularization is also something that is important. Suppose we have a perfect set of weights, so our loss is 0. The problem is that this set might not be unique. There can be multiple sets of weights that give the same loss. And to distinguish between 2 such sets, we extend the loss function with a regularization penalty. So the loss is 1 divided by the number of training examples and the sum of the loss for each training example, plus some constant multiplied by the regularization loss for the weights. And the most common one is the L2 norm, which penalizes large weights, since large weights can lead to numerical overflow and numerical instability. And small weights improve generalization and reduces the problem of overflow. So the L2 norm is calculated as the squared sum of all weights. So we just square all weights and we'll calculate the sum of the squared weights. And the parameter, the lambda parameter, is called the regularization strength and is typically set to a low value such as 0.01. So if we have the set of weights as in the previous example, then we square all the weights, we get a new matrix, and then we calculate the sum of all squared weights, and that's our L2 norm or regularization, which is 0.8166. And the total loss for our example is the data loss. That's what we calculated before, 1.04 plus the regularization loss, which is the lambda parameter multiplied by the squared sum of the weights, which is 0.01 multiplied by 0.8166, which we calculated before, and the total loss is 1.048. So, a more complete example, we have 3 categories and 2 input attributes. So our weight matrix will have 3 rows and 2 columns, and we have a bias vector, and we have a number of input examples, 9 in this case, and each input example has an actual category. So the first 3 examples belong to category 0, the blue, the next 3 category green, 1, and the last 3 category 2, red. And the scores, we can calculate the score for each of the input examples. Now I've modified it a bit, so each input example corresponds to a row in the scores matrix here. So the first set of rows is 1.30 minus 1.10 and 0.60, and we can just do the matrix multiplications plus the biases, and then we will see that we will get these scores. And the loss in this case is 0.56, and we continue with the second training example and calculate the scores. Now we have a new loss, 1.04, and after we have iterated over all training examples, we can calculate the mean loss, which in this case is 1.84. That's the data loss. And regularization loss, the squared weight, sum of the squared weights is 35, and the lambda parameter 0.01, so the regularization loss is 0.35, and the total loss is the sum of those, 2.90. Optimization or training, that's a very important step for our classifier, obviously. The loss function quantifies the quality of a set of weights. But the goal of optimization or learning is to find a set of weights that minimizes the loss function. And this can of course be done with random search or hill climbing, but it will most likely take ages to find a good set of weights. Instead, we can compute the best direction of the weights using the gradient of a loss function. The task is to compute the best direction in which we should change the weights. And this direction turns out to be related to the gradient of a loss function. The gradient is a vector of slopes, the derivatives for each dimension in the input space. Mathematically, the derivative of a 1D function with respect to its single inputs is, if you remember from the calculus, this is the definition of the derivative. If we have a function that takes a vector of numbers instead of a single number, the derivatives are called partial derivatives. And the gradient is simply the vector of partial derivatives in each input dimension for each attribute in our inputs dataset. And we can calculate this vector of partial derivatives in two ways: numerical gradient, slow and approximate, and analytic gradient, fast and exact, but it can be a bit error prone. And since speed is important, we will focus on the analytic gradient. To find the analytic gradient, we need to derive a formula for the gradients using our math skills. Luckily, the loss functions we use are well known, and we don't have to find the formula on our own. We just have to look up which function we use, and then we can see the derivative of that function. And depending on the loss function, the formula can be quite complex to implement. So, how can we implement the gradients formula for Softmax? So, this is what we did so far. We have calculated the scores as a matrix multiplication plus bias vector addition, and we calculate the log probabilities, and when we normalize them, and we get the resulting normalized log probability vector as before. This is what we did when we calculated the loss. And we continue by taking the normalized vector, and when we update the score for the correct category yi by -1. And since we know from this training example that the correct category is category 2, the red one, we update the third value 0.353 by -1, and we get a new gradients vector called d-scores. And we then multiply the d-scores vector with a transpose of the training example. And now we get dv, that's the difference in weights, how the weights should change to move closer to the training example. And to multiply a column and a row vector, we get a matrix. So the first element in the resulting matrix is the first value in d-scores multiplied by the first value in the row vector. The second value is the first element in the d-scores vector multiplied by the second value in the input row vector. And we continue doing like it's shown here. And then we get the resulting dw vector, that's the difference in weights, how we should change the weights. And we also need to know how we should change the biases, and it's simply summing the values of all rows in the d-scores matrix into a new vector. And since the d-scores is a vector in our case, since we only had one training example, db is equal to the d-scores vector. So now we have the gradients, and the gradients show us how we should update the weights to move closer to the training example. If we have multiple input examples, it's not that much more complex. We have a multiplication of the weight matrix with the input matrix, and we have a vector with the correct categories, and we add the bias vector to each column in the resulting matrix from the multiplication. And we now get a scores matrix instead of a scores vector. So the first column, that result from multiplying the weights with the first training example. The second column in scores, that's the result of multiplying the weights with the second training example. And then we calculate the log probabilities and normalize them as before. So the normalize is now a matrix instead of a vector. And we calculate the d-scores matrix, where we simply update the correct score for the correct categories iy by -1. So in the first column it's the red value we need to update, and in the second column it's the green value we need to update. And then we have to divide by the number of training examples, 2 in this case. So we divide all values by 2, number of training examples. And now we have a matrix multiplication instead of a vector multiplication, but it ends up in a matrix of the same size, where we have one value for each weight in the weights matrix, and they correspond to how we should change the weight to move closest to our 2 training examples. The biases should be changed by, we just calculate the sum of all rows in the t-scores matrix, and now we get a vector defining how we should change the bias values. We also need to add a regularization factor to the weight gradients dw, and this is done by adding the weight matrix w scaled by the regularization strength lambda divided by 2. So let's go back to our first example with a single training example. We have the dw, that's the gradients we calculated, plus the weights matrix multiplied by lambda multiplied by 0.5, and that equals to a new matrix where we have added the regularization strength. So it's just add each scaled value of w to dw matrix. And the biases is not changed, for regularization is only affects the weights. And finally, we need to update or upgrade the weights. The weights are upgraded by subtracting dw multiplied by a learning rate. The learning rate is typically set to a rather low value, such as 0.1 or 0.05. And the best learning rate for each dataset has to be discovered by trial and error. So we have our set of weights, and we subtract the gradients dw multiplied by the learning rate, and we have a new set of weights. So the first element in the new set of weights is the first element of w, 0.01, minus the first value in the gradients matrix, minus 0.2317 multiplied by 0.1, and we get a new value 0.033. That's the updated weights. And the bias is upgraded in the same way. So we have a bias, the old biases minus the dB, the change in biases, multiplied by a learning rate, and we get a new set of bias values. And if we calculate the loss for the new set of weights and biases, we can see that it has decreased from 1.044 to 0.48. And the goal is, of course, to have as low loss as possible, so that's good. So the previous example we had, it looks like this. So now let's calculate the gradients. And if we calculate the gradients with all the regularization, loss, etc., we see that how the weights will be updated. So the first weight will be updated by minus 0.20, and the second by 0.07, and the bias will be updated by 0.15. So that's how we should change the weights and biases based on the training examples we had here, the 9 training examples. That's the first iteration. In the second iteration, we now have a new set of weights. The first weight is 1.02, because we upgraded it by minus 0.20. And now we get a new set, we have a new set of weights, and we have a new change in weights, how the weight should be updated to the next iteration, and we see that the total loss was reduced from 2.19 to 2.16, the data loss from 1.84 to 1.81. And this procedure of repeatedly evaluating the gradients and perform weight updates is called gradient descent. And it is the most common way of optimizing or training linear classifiers and also neural networks, which we will look into shortly. We can also train on batches of the training examples instead of all examples, usually called mini-batch gradient descent. Or we can train on one example at a time, which is usually called stochastic gradient descent. So the information flow looks something like this. We have the weights, we have the inputs with the corresponding class labels, we calculate the score function, we calculate the data loss and the regularization loss from the weights, and then we update the weights to a new iteration. So now we actually have a complete linear softmax classifier. Let's see how it works on the example data, which we have in our example are nine training examples with corresponding categories, and then we start training. So at the first iteration we had a loss 2.19 and the accuracy 2 out of 9 training examples were correctly classified, so we had an accuracy of 22.2%. And we have a lambda regularization strength of 0.01 and a learning rate of 1. In the next iteration 1, we have a reduced loss 1.91, but still only 2 out of 9 examples were correctly classified. And we continue, and on iteration 19 we had a loss of 0.63 and all examples were correctly classified, so we have 100% accuracy. On the iris dataset, we have a learning rate of 0.1, a regularization strength of 0.01, and we continue on 300 iterations, and we see that the loss is reduced from iteration to iteration, and the final result, we have an accuracy of 147, correctly classified instances of 115 total, so an accuracy of 98%. The next question is, how can we expand this into a neural network? The current network layout looks like this. We have an inputs, two inputs x0 and x1, and we have a single layer, the output layer. So the inputs are connected to the output layer, the softmax output layer. And each node in the network is called a unit, so we're 3 units in our output layer. And we have a network with 2 input units and 3 output units. So the limitations is that even if this is a quite powerful classifier, it can only handle categories that are linearly separable. So in this example dataset, the spiral dataset, the linear classifier will never be able to learn correctly from this data, so we'll always get a quite bad accuracy. To solve this, we need to expand the network with a layer of hidden nodes, of nonlinear nodes. And the layered, or what we usually call neural network, can learn categories that are not linearly separable. Each unit in the network has its own set of inputs, a weight for each input and a bias. And the output, the score, can act as input to units in another layer. So the input data X is the input to the hidden layer, but the output layer instead has the scores from the score function of the hidden layer as inputs. So the training data attributes is inputs to the hidden layer, and the scores from the hidden layer acts as input to the output layer. And in the output layer we used the softmax function, and in the hidden layer we need a slightly different type of activation function. And there is a wide range we can choose from. The quite old and common one is sigmoid. You can also use one called tan-h, but the most common one today, and the one we will use in our example, is the ReLU function. ReLU, or rectified linear unit, calculates the function f of x equals max, 0, and x. So first, the weighted sum of the inputs plus the bias is calculated as we've done before. Then the activation function is applied on the result. That's a max function, so we'll never get any negative values. So in the hidden layer, we calculate the weight matrix multiplied by the input vector plus the bias, and we get a scores of a hidden unit. That's the same as we did previously. And the scores is a vector with 3 values because we have 3 categories. And then we apply the ReLU function, and the ReLU function only updates the first value since it's negative, and the ReLU is a max operation between 0 and the score. And the output layer has its own set of weights. Now we only have 3 columns because the output from the hidden layer, the ReLU vector, only contains 3 values. And we add the bias vector, and now we get the output scores from the output layer. And when we apply the argmax operation, we see that this example is classified as the first category, the blue category. The loss function or gradients are slightly more complex. We need to calculate the loss and gradients for the output layer first in the same way as we did before, and the gradients are then back propagated into the hidden layer, and the loss for both layers are summed. So what we did before is that we had the output layer, we have the scores, and we calculate the log probabilities, and we normalize the log probabilities. And we calculate the loss, which is 1.41. That's exactly what we did before. And we calculate the d-scores. We update the score for the correct category, which is red in this case, by -1. We multiply by the transpose of the input example, and now we get a new set of weights, which we use, or dv, the way we should change the weights to get closer to the training example. And the db is the sum of the rows, and since we only have one training example, db equals d-scores. That's what we did before. The output layer is exactly the same as the linear softmax classifier. The hidden layer has its own set of weights, and loss in this case is the L2 regularization, the sum of all squared weights in the weights matrix, and divided by 2 and multiplied by the lambda. So in this case the loss is 0.00408. The gradients, we calculated the d-scores, from the output layer, and the weights from the transpose of the weights from the output layer. We calculate the d-hidden, the gradients in the hidden layer. That's the transpose of the weight matrix from the output layer multiplied by the gradient d-scores vector from the output layer. And that's equals the d-hidden vector we have here, so with 3 values. And when we apply we use the ReLU activation, and the ReLU activation, as we saw before from the hidden layer, is 0, 0.86 and 0.28. and we update the gradients vector of d hidden by setting all elements to 0 if the score function in the corresponding element is 0. So we set the first value to 0 because we have 0 on the first element in the ReLU activation vector. And when we multiply the gradients vector with the transpose of the input values, and this is since we are in the hidden layer, that's the inputs from the training example. In the output layer we have the inputs, in that case was the outputs from the hidden layer. And we get the dv matrix, which is how we should change the weights to get closer to the training example. And the db is the sum of the rows in the gradients vector d hidden. And then regularization is added to loss and gradients in the output and hidden layer exactly as before. And the total loss is the loss for the output layer plus the loss for the hidden layer. And the weight upgrades works the same. The weights for the hidden layer is upgraded by taking minus the gradients multiplied by the learning rate 0.1, and we get a new set of weights. Biases works the same. We update the bias values by taking minus the gradient biases multiplied by the learning rate, and we get a new set of biases. So the linear classifier has now been extended to contain a hidden layer with non-linear ReLU nodes. And the hidden layer enables the classifier to learn categories that are not linearly separable. For example, the spiral training set. We're going to look at an example. This is an application I created where we can visualize the boundaries and decision boundaries and how they learn from training data. So if we take the simple demo data set where we only have 9 examples in 3 categories, we see that the linear classifier is quite quickly able to learn from this data to get 100% accuracy. But if we instead take the spiral dataset looks like this, we will see that the linear classifier will never learn completely. It tries, but it will always end up around 50%. It cannot learn any better because it cannot learn boundaries that are not linear. We can also look at the circle example, and if we train here we will see that the linear classifier will always output one class for all input examples. So the accuracy will always be 68.6%. But if we instead use neural networks on the spiral example, we will see that neural networks here the decision boundaries will move closer to a perfect classification, and more examples will be included, and we see that it can actually learn fairly well, 99.3% in accuracy in this dataset. We can also see in the circle example that the neural network quite quickly learns to place a decision boundary around the blue circle in the middle, getting an accuracy of 100%. We also had the flame example looking like this. If we train a neural network classifier on this, we will see that it quite quickly learns to a decision boundary that is fairly good for this dataset. This dataset, however, is slightly complex even for neural networks, because the decision boundary has to change quite a lot. We need to go up around the blue area here, and we need to go down around the red area here, and the loss is changed is only changed by a small margin if the boundary is moved. So the classifier actually, the neural network classifier actually stops around an accuracy of 96.2%. It never really learns because it needs to change the boundary quite a lot and for little gain. We can also look at deep neural networks, in this case where we have 2 hidden layers instead of 1 hidden layers, and we see that the deep neural network classifier also learns the spiral dataset very well. Our last example is k nearest neighbor, where we classify each example as the most frequent category in the k nearest examples. And we see that in the demo example, it learns very well, or learns. The k nearest neighbor actually doesn't learn, it just looks at the nearest examples. But it works very well for the demo dataset, and we see that the boundaries here can be quite complex, the decision boundaries. Especially if we look at this dataset, it takes a while for the nearest neighbor to classify this, but we see that it can create extremely complex boundaries in this dataset that neural networks are not able to. If we look at neural networks on this dataset, we will see that it will not be able to learn such complex boundaries. And the KNN for the circle dataset works well, and for the flame and the toy problem as well. The drawback is, of course, for k nearest neighbor is that classification time is extremely slow, since we don't do anything at training time. So, neural networks are able to learn non-linearly separable categories, and in many real-world examples we don't have any clear linear separation between categories. But neural networks are more complex and they take more time to learn, so if we have perfect linearly separable categories, then we don't need a powerful neural network, then we are satisfied with just using a linear classifier, which are faster to train. So choosing the correct type of classifier for your type of dataset is the most common problem in applied machine learning, applying the right algorithm for your dataset. So that was everything I had to say about neural networks. Thanks for listening.